we're going to look at geometric sequences. So we already talked a little bit about sequences. Remember the word sequence? Sequence just means ordered list. When we talked about arithmetic sequences, that was where we had things growing by a common difference each time. So I was adding a constant. This time I'm going to be multiplying a constant to get from one term to the next. And because I'm multiplying now, I'm not going to use the term common difference anymore. I'm going to use the term common ratio, right? Because I'm multiplying by some ratio or dividing. And I'm going to use R to denote that variable. So if I look at the following sequences, I notice they're definitely not arithmetic, right? Because I don't have a constant pattern. If I was to go from 2 to 10, I'd be adding 8. 10 to 50 is adding 40. So because it's not a common difference, it's not the same jump in terms of addition each time, it's not arithmetic, right? It is a sequence. It's an ordered list of numbers. But if I go from 2 to 10 through multiplication of not 4, 5, and I go from 10 to 50, I'm multiplying by the same amount. So I'm increasing, I'm growing, but through a common ratio or a common multiple, right? And so the next term, if I multiplied by 5 again, I would get 250, right? Multiply again, 1,250. And so my R value is 5 because I'm multiplying by 5 each time. If I look at the next one, to get from 3 to -6, I'm multiplying by -2. And then to get from -6 to +12, I'm multiplying by -2 again. So notice because I'm multiplying now, if I include negatives in there, it's going to alternate the sign every other term. Right? Next term would be -24, then +48, then -96, right? And so that just puts a negative on my R value. Things are still growing, right? The numbers are still growing, but I have a negative value. If I'm looking at this last one, so I'm going from 12 to 3 and 3 to 3/4, right? That is me dividing by 4, but in terms of a ratio, I can say that that's 1/4. And so my R value is 1/4. And if it's a struggle to identify that, especially with some of these fractions, it can be tricky. I can always find the common ratio by dividing any term by its previous term, maybe by the previous term. Right? For common differences, we subtracted because I was trying to find that what am I adding each time. This time I'm dividing because I'm saying what am I multiplying by each time. And so I can denote that again by saying any term divided by the previous term, right? This is my nth term, n minus 1 is one term right before it. So for example, I could look at something like this, right? If I did 3 divided by 12, it gives me 1/4. If I did 3/4 divided by 3, right? Well, that's the same thing as 3/4 times 1/3. The 3's cancel out. It's still 1/4 from any term to the next term, as long as I put the further term along on the top and the earlier term on the bottom, the previous term on the bottom. So in general, we did this with arithmetic sequences. I have my first term, my second term, my third term. Let's say I have like my 10th term and my 57th term. And then in general, my nth term. So I could describe any term. Well, the first term is going to be T1, right? My first term is whatever it happens to be. I need to kind of know that term to do a lot of this work. I need to know where my sequence starts. But then my second term, well, I increase it by multiplying by a common ratio. So I get T1 times R. My third term, I get T1 times R times another R. And that's not 2R, right? It's not R plus R. So what that is T1 times R squared. And so just like with arithmetic, we kind of start to recognize this pattern between what term number I'm on and how many times I'm doing that jump, right? How many times I'm introducing my common difference or my common ratio in this case. And so on the 10th term, I have to multiply by R 9 times. And so I get a power of 9. On my 57th term, I have 56 common ratios. And so in general, on my nth term, I have T1 times R to the n minus 1, right? Because I only start to multiply by R once I get to my second term. I start from T1 and then I adjust from there. So my general term formula is that T of n is equal to T of 1 times R to the n minus 1. Keeping in mind all of those orders of operations, right, where exponents have to happen first and then multiplication can happen, right? It's T times that. The power is not on the T, it is on just the R. Where, just like before, T1 is my first term, R is what I call my common ratio, N is the number of terms, and then Tn, I can describe it a few different ways. Either it can be a general formula, so we call it general form, which again is like a tailored formula. It's specific, right? So you sub in n and, oh sorry, not n, T1 and R, because those aren't going to change, right? It doesn't matter if I'm talking about the 8th term or the 8,000th term. The first term is still whatever the first term is, and the common ratio between terms is still the same. And then I simplify. And so what that gives me it gives me an equation for T of n in terms of n, right? So it's like a y equals mx plus b kind of situation. It's like I have my y and my x, where this is like my y value and this is like my x value, my dependent and my independent variables. Right, so it would be something like this, right? T of n is equal to 2n plus 1 or something, right? It might simplify down to something like that. N minus 5, 2n minus 5, right? Depending on the situation we're in, depending on that R and that T1 value, right? Where it's just an equation with my dependent variable and my independent variable as the only unknowns. Or I can specify an n. I can say, tell me the 8th term, tell me the 19th term. Right, so it's the value of T of n given an n value. Right, so T of 8 is some number, right? So here's a sequence. Let's find T9. I want to find the 9th term. So first thing to check is what kind of sequence am I dealing with, right? We're in the geometric sequence unit, so it's going to be geometric, but I could always double check. Is it arithmetic first, right? I could check what's the addition from one to the next. Is that in common between every term? Or should I be focusing on multiplication instead? Right, and in this case, it's times 4 and then times 4 again, so it's geometric. All that means is that tells me which formula I'm going to use. My geometric formula says T of n is found by taking T1, multiplying it by R to the n minus 1. So I ask myself, what are all these things? Do I know the first term? Do I know how many terms I'm dealing with? Do I know my common ratio? And do I know the nth term? Right, well, my first term is 3. I want to deal with 9 terms because I want to find T9. And my R, as I just found, I multiply by 4 each time. So I'm going to plug all these things in. I want to find the 9th term. First term is 3, R is 4, to the 9 minus 1. I can type this all in my calculator, but again, if you're doing it by hand or if you're doing it piece by piece, just remember your order of operations. I'm not doing that 3 times 4 first. I'm doing 3 and I'm multiplying that by whatever the result of 4 to the 8 is. And so I punch this into my calculator. 4 to the power of 8 is like 65,536. That times 3, or if you type it all in one go, is 196,608. So if we notice, geometric sequences grow really quickly, right? When I'm increasing through multiplication rather than just addition, things grow a lot quicker. So let's look at another sequence. Check if it's geometric. Say I'm multiplying by 4. Is that constant? Yes, I'm going to multiply by 4 each time, right? And I need at least 3 terms to help me identify if something is truly a pattern like that. So if I want to find the 12th term, I start at 2. I want to find 12 terms. My R is 4. And I want to find T12. So I plug it all into the same formula. So now I'm doing 4 to the power of 11 and multiplying that by 2. And the 12th term is 8,388,608. Right? And so again, really big numbers, especially as I get further along. The 12th term here is already in the millions. The next term, the 13th term, is already 8 million times 4. So we see that huge growth. If I want to talk about the general term, I take my exact same formula. I still put in T1. I still put in R. And I have this equation here, right? Where this is fine, but we have the ability, we have the skill set to simplify this a little bit more, right? I'm looking at 2 things. They technically both are exponents, because this I could call 2 to the power of 1. And I remember that the only exponent rules I have when I'm multiplying 2 things is that they have to have the same bases. And right now they don't. But I could rewrite 4 as 2 squared. I can use that power rule here, right? Which remember is x to the m to the power of n, is I multiply those powers. So here's what I'm looking at. 2 to the 1 times 2 to the 2n minus 2. Right? And then now I can apply this rule with these. I have 2 to the power of 1 plus 2n minus 2. And so to simplify that fully, I have 2 to the power of 2n minus 1. And so that's a fully simplified equation, right? While this is okay, this is really good. This is great. This is fully simplified to the best of our ability. We don't explore these types of functions a ton in Math 20. These are called exponential functions, but we will dive into these a ton in 30-1. So if I want to find the first term, I need to know all those other things, right? If T1 is what I'm trying to identify, I need to know how many terms I'm dealing with. I need to know my common ratio, and I need to know the value of some other term. So I know a couple, right? I know 4 and 5,000, or I know 7 and 40. I could work with either. I'm going to go with 7 and 40 because why not? But here I'm stuck because I need to find T1, so that has to be my unknown, but I also don't know R. So let's think about the difference between these 2 things. If I know my 4th term is 5,000, there's term 5, there's term 6, there's term 7. I know that to get from T4 to T7, I've had a common ratio of R 3 separate times. So what I know is that if I take that initial value, that 5,000, and I multiply it by R cubed, that gets me to an end result of 40. So now I just have a little power of 3 equation to solve, right? I can divide both sides by 5,000. So R cubed is this reduces down to 1 over 125. Then I cube root both sides. Cube root of 1 is 1. Cube root of 125 is 5. And so r is 1/5, right? Or 0.2 as a decimal. Right? And notice what happens when r is a number less than 1. I see that my values are decreasing as I move along this sequence. So now I know my value, r is 1/5. I have one unknown. I can plug everything into this formula. So t of n is t1 times r to the n minus 1. Again, at this point, you could use 5,004 or you could use 7 and 40. I'm just going to go with the smaller numbers. T1 is what I'm trying to solve for. R is 1/5. And I'm raising this to the power of 6. Right? So before I divide it, I have to do that exponent. I have to evaluate this. So 40 is T1 times 5 to the power of 6 is 15,000. So this is 1 over 15,625. If I multiply both sides by that, it isolates T1. So I'm going to multiply 40 by 15,625. And I get a T1 value of 625,000. Which makes sense, right? Because if I'm cutting this thing into a single fifth, right? If I'm taking only 20% of this value each time, by the 4th term, I'm at 5,000. By the 7th term, I'm at 40. It makes sense that I started at a much larger number. All right, and then the application problems. So a Dodge Caravan, quality minivan, is bought for $27,000. It will depreciate by 8% from its previous value each year. So depreciate is a loss in value. But keep in mind, I want my R value to be the remaining value. Right? I want my R to tell me exactly how much it's worth. And so if I'm depreciating by 8%, I'm looking at 100% minus 8% each year. So I have a remaining value of 92%. So R, if I divide my percentage by 100 to write it as a decimal, R is going to be 0.92. Again, a value less than 1 will cause my fractions to my terms to get smaller. An R value greater than 1 makes things grow. So if I had a sequence, I would write it something like this. It starts at $27,000. I find the next term by saying, okay, next year, I take $27,000 and I say, what's 92% of that, right? I lose 8%, so I'm left with 92%. And so next year it's worth $24,840. I'm going to find one more term. I'm going to multiply this by 0.92 yet again. I'm going to find $22,852.80, right? You should show at least 3 terms in a sequence just so that pattern is clearly recognizable. And so I want to find out how much this minivan is worth in 7 years, right? I've spent my time with it. I'm ready to sell it. Let's see how much it's worth. Key thing here is it says after 7 years. What that means is that realistically, my second term is actually after 1 year. Because when I buy it at $27,000, I haven't already lost any value yet. A year hasn't passed. So 2 years happens at term 3. And so you see that kind of pattern again. If I want to talk about how long something or how much something has changed after 7 years, I want the exponent to be 7, right? I want to see r to the power of 7 after I've done any sort of simplifying, because that's what that means, right? I want to see this value change 7 different times. So when I go to set up my equation, My first term is 27,000. I'm going to be looking at 8 terms because I'm including year 0, right? It's like that idea of being inclusive of zeros. R is 0.92. I'm finding the value of the 8th term, which is 7 years of depreciation. So T8 is 27,000 times 0.92 to the 8 minus 1. So that's where that 7 comes in, right? I'm finding 92% of its value 7 different times. And so when I plug that in, when I do 27,000 times 0.92 to the power of 8, or to the power of 8 minus 1, power of 7, I get $15,061 and those 86 cents. Don't forget your 86 cents. We know that it's a dollar amount, so I'm going to round like it's a dollar amount. So in words, in 7 years, the minivan is worth $15,061.86, right? Or $15,062. So similar situation, you buy a home instead. Your home appreciates, right, or increases in value. What a great investment in real estate you've chosen to make. By 6% each year. So now I'm at 100% plus 6% each year. So 106% as a decimal is 1.06, right? Again, a number bigger than 1 will increase my terms. I want to find the value when I sell 12 years later. So I want my power to be 12. Therefore, I'm looking for the 13th term. Right? Because again, I have my initial value as my baseline, as my first term. So T1, $415,000. N is going to be 13. R is going to be 1.06. And T13 is what I'm looking for. So my first term, and I see that increase in value, 1.06. I see that happen 12 times, right? 12 years later means including year 0 when I moved into the house. So I punch that into my calculator. And wow, did I make a great choice investing in real estate. $835,061, a weird coincidence again, and 54 cents. Realistically, the house is worth $835,062 in 12 years. Lastly, let's look at Canada's population growth. In 1990, the population was 26.6 million. The expected population in 2025 is 38.4 million. So when I say what was the annual rate of growth, I'm asking for my R value. Right? I'm trying to figure out what is R. I know I started at 26.6 million based on if I'm starting in 1990. R is what I want to find. I know the value of my last term, right, in 2025 is 38.4 million. But again, when I do 2025 minus 1990, right, it's 35 years, but I need to be inclusive of the fact that 1990 is included in this situation. Right, so I'm talking about T36, I'm talking about 36 years, because if I include 1990, right, And if that's hard for you to understand, if 1990 is year 1, and 1991 is year 2, and 1992 is year 3, right? You see that discrepancy between the year number and what term number I'm on. So if I want to find the annual rate of growth, I know I end at 38.4 million. I start at 26.6. I'm trying to solve for R here. 36 minus 1, right? That's where that 35 is coming into play. I need to divide both sides by that 26.6 first. So when I do 38.4 divided by 26.6, and again, I can keep these as decimals. I don't have to write it as 1 million because I can keep the units as millions. So that's R to the 35. Now I take a 35th root, right? Which is the same thing as a power of 1 over 35. But I punch that into my calculator. And I get 1.0105, yada, yada, yada. We want to keep as many decimals in our calculator if we want to use this number again. But this means that my R value is about 1.01, which is approximately 1% growth per year. Right, times 100 is 101%. It means the value that I have each year is 1% more than the value I had in the previous year. What is more like what was the expected population in 2017? Well, now I know. Again, I can start from T1, 26.6. I now know my R is 1.0105. I'd keep at least this many decimals if you don't already have it stored in your calculator memory. I want to figure out what year this is. Same thing as before, right? From 1990 to 2017 is 27 years. So I'm actually looking for the 28th term because I need to be inclusive, right? I've jumped forward 27 years. My power on R should be 27. So I'm going to take 26.6 times 1.0105. And again, I'm going to use in my calculator, I'm going to take that full string of decimals, the 1.010545, blah, blah, blah. And then 28 minus 1, or 27 years in advance. So I take the number in my calculator, I raise it to the power of 27, and then I multiply the result of that by 26.6. And so if your number's a little different than mine, double check that you used the full string of digits. I get 35.3 million people. And so that is our population in 2017, or that was what they expected the population in 2017 to be. And so that's geometric series. That's geometric sequences. We're going to start geometric series in the next lesson.